Hey, it's Nordy coming at you from my closet with Carl, who will probably be here most of the video. I wanted to show a break-in that I found especially interesting enough to make a video for this puzzle called Hopscotch, which is a variant Sudoku with a few rules, and we're just going to jump right in. The first rule is normal Sudoku, which means place the digits 1 to 9 in every row, every column, and every 3x3 box. And it now has some special rules. The first is whisper squares. So every 3x3 box contains one hidden 2x2 region called a whisper square. So here's a 2x2 region. In a whisper square, orthogonally adjacent digits, like so or like so, must have a difference of 5 or greater. So that means, let's say this is an 8. The digits that are next to it, orthogonally, must have a difference of 5 or greater. So possibilities for this digit are 1, 2, 3, but not 4 because that has a difference of 4 and not 5. So let's say it's 3. The similar relationship here, 8 has to have a difference of 5 with this square, so this could be a 2. And now this square is adjacent to this one, and it must have a difference of 5 or greater with those, so this could be a 9. So this is a valid whisper square. Now, whisper squares, wherever we place them, must not touch orthogonally, but they may touch diagonally. So if we have a whisper square here and we're thinking about where to place it in this box, it cannot go here because that would be next to this square. We can't squeeze it into here, so it can't go here. So it must go somewhere up here, and maybe it goes here. So this is how the geometry of placing these in here works. The final rule is equal sum cages, which means that within each cage, so here's a cage, the sum of digits that are inside whisper squares, so here's a digit inside a whisper square, equals the sum of digits outside whisper squares. So if in box 5 the whisper square is here, what that means for this cage is this digit, which is in a whisper square, has to equal the sum of these digits here. So these could be something like 4 and 5, because 4 plus 5 equals 9. These are outside, this is inside. Totally valid. So those are the rules. If you want to solve yourself, you can try a link which I'll include below. Otherwise, let's try to break in. So the first thing to do in order to break in is to just learn a little bit more about whisper squares and sort of what's going on with them. So if we were to put a square here and try to fill in the digits. If you're familiar with German whisper lines, what happens in these whisper squares is there's kind of like a looped square whisper line that's contained in there. So you can think about it like that. And what's going to happen is we're going to have to place some digit here. Let's say it's 8. And once we place a high digit, in order to get a difference of 5, what we're going to have is a digit like 1, 2, and 3 is possible. 1, 2, and 3 is possible for being adjacent to 8. This can't be 3 for Sudoku. And so wherever we place the high digit, it's going to be surrounded by low digits. And this digit here is then going to be forced to be high. So we're going to have this checkerboard pattern of possibilities where we have high digits in one diagonal, low digits in the other diagonal. And thinking about what these can even be, the high digits generally in German whispers can be 6, 7, 8, or 9, because you can make a difference of 5 with these numbers. And the low digits are 1, 2, 3, and 4. 5 can't ever go on a German whisper line because it can never have a high enough difference with another number. But let's think about what happens when we try to put 6 here. Well, 6 actually is going to cause some problems because the only number that can go next to 6 is 1, and we can't place a 1 in both of these. So, in fact, from the set of the high numbers, we can remove 6 as a possibility. Similarly, from the set of low numbers, 4 isn't going to work. 4 requires 9 and 9, so 4 isn't going to work. Now we know basically what's going to happen whenever we place any whisper square into the grid. It's going to look like this, possibly rotated, and it's just going to be somewhere in here with this arrangement of low and high digits in a checkerboard. If we take the general case, let's say just a general case, the candidates for the general whisper square are 1, 2, 3, 7, 8, 9, which is a sextuple. Not sure about the vocab there. So in any whisper square that we place is going to have these possible digits. So if we place in this box here, we're going to have 1, 2, 3, 7, 8, 9. 1, 2, 3, 7, 8, 9, and they're going to be in a checkerboard somehow. So that's the first main fact about these whisper squares. The second fact is geometry, which is if we place a whisper square into a box, wherever we place it, say they're here, here, and here, there's an interesting fact about what happens with this row that cuts through the middle of the box, which is that because we're placing a whisper square somewhere in here, there's going to be two cells. Doesn't matter if we place it here, here, or here, or here. There's going to be two cells contributed to sort of this center row from this whisper square. Similarly here, here, and here, so that in this row, we're going to have 6 whisper square cells just guaranteed to be in that row somewhere. Well, we don't know where they are, but they're in there somewhere. And so this has to be a 1, 3, 7, 8, 9 sextuple in this central cut. And that's going to be true for this cut. That's going to be true for this cut. You know, these rows here, 2, 5, and 8. And similarly for these columns. Wherever we place the whisper square, we're going to be left with 6 whisper square cells in each of these rows somewhere. And that means whatever cells are not part of the whisper squares are going to have to be 4, 5, and 6. So in these special rows, I'll call them special rows and columns, we're going to be left with 4, 5, 6 triples wherever there aren't whisper squares. And that's very important because that allows us to think about what happens in this box. Where do we place the whisper square? Well, it can't go here. And the reason it can't go here is because this cage needs a outside whisper square in order to make the sum work. You know, you can't add up all the whisper square cells and have it equal. It just doesn't make sense. Basically, you need a cell that's in a whisper square and you need cells that are outside the whisper squares in order to have an equal sum. Otherwise, the sum of the squares outside is 0, so this breaks. Now we can think about, you know, if this doesn't work, well, it has to go here, here, or here. But let's see what happens if we try to put it here. If we try to put it here, we know that in a special row, any non-whisper square cell, like this one, because it can't be in the whisper square now, is going to be a 4, 5, or 6. You know, and even I think filling it in is just helpful to see how this works. So this square is going to be a 4, 5, or 6 if it's not a whisper square cell. But now if we're trying to add up 2 whisper square cells to get this one, we're going to run into a problem because one of these has to be a high digit, 7, 8, or 9. One of these has to be a low digit. And the lowest we can make both of these is 7 and 1, which means we'll never be able to make this sum. So actually the whisper square cannot go here. Otherwise, we're not going to have a valid sum. Similarly, if it can't go here and take these two, it also can't go here and take these two, because we're going to have it run into this similar problem with this cell. So the only possible square left, or the only possible place left for the 2 by 2 is here. And once we do that, we can rule out all of these cells as being whisper squares because they're orthogonally adjacent. And because these are in their special rows and special columns, these have to be 4, 5, 6. And this digit, whatever digit it is, has to be the sum of these two digits. And the smallest we can make these is 4 and 5, which happens to be 9, and we get our first digit. And now, since this is a high digit, it needs 2 low digits next to it, 1, 2, and 3, and this can't be 3. And this needs to be a high digit, 7, 8, and it can't be 9. So I'm just going to flash these just to show how that works. So we've placed the first square in this box, knowing that whatever's in the special row that's not on a whisper square has to be this 4, 5, 6 triple, forcing the sum to be 9. And now we can look in a couple different places. We can kind of see, you know, what's going to happen in this region or this region, because they're kind of, you know, affected by where this is placed. And I'm gonna go here because we're restricted on where we can place the whisper square now. So we're thinking about where to place it. If we place it here, we run into some problems because now this can't be a whisper square. So these two have to add to this, and we've proved that 2 whisper square cells cannot add to a non-whisper square cell that's in a special row. So this placement doesn't work. So the whisper square has to go here. And now we can think about what this digit can be. If the whisper square in box 5 is, say, somewhere here, we know that these are going to be non-whisper square cells. They're in a special row. They can only be 4, 5, and 6. Between this, the only way to make 4, 5, and 6 add to a valid number is to use 4 and 5, which would have to force this to be 9, but that breaks. So what that means is this this cannot be a non-whisper square cell. This has to be a whisper square cell, which forces this to be a whisper square cell. And now, once this is a non-whisper square cell and we have to sum to it, the only way to get to a number here, 4, 5, or 6, is to use 2 low digits. So these are going to be 1, 2, and 3. We'll get our checkerboard pattern here for this whisper square. And now, between 1, 2, and 3, you can't make 6, because 6 would require 2 3s, so this becomes 4, 5. And we have now a whisper square placed in box 4. We can do our geometry, kind of surround it with this layer that blocks out future whisper squares. And we have 2 whisper squares now. We can use similar thinking to place a whisper square here by noting that once we have this barrier, we're going to have a whisper square here, which is going to create another barrier here, and we're going to have to place a whisper square in this box either here or here. We prove that this breaks because the sum won't work, so the whisper square has to go here, and we can surround it with our barrier. This is going to force a whisper square down here, so we can surround it with our barrier here. And now we'll have a whisper square here and here. And this brings us to the final interesting fact about the whisper squares, which is thinking about what happens when you try to place all of the whisper squares sort of in the same 2 rows or the same 2 columns. So we know that whatever's in these whisper squares, wherever we place them, is going to be 1, 2, 3, 7, 8, 9. And we can think about Well, now what's going to happen when they're all lined up? When they're all lined up, we're going to have sort of 6 of these numbers that need to appear here, and these numbers need to appear here. So a 1 has to appear, you know, in this section of these whisper squares, and a 1 has to appear in these section of whisper squares. So there's going to be 2 1s, 2 2s, 2 3s, and so forth. So we're going to have to place 2 3s somewhere in the whisper squares. Let's say we place them here, because we know there's going to have to be 2 3s somewhere. Similarly, there's going to have to be 2 7s somewhere in these whisper squares. And so, you know, we can place one here, let's say in this box, but then we need to place one in one of these boxes, and we're going to run into a problem because a 7 can never go next to a 3. And since we have this sort of checkerboard pattern, if it's a low digit, it has to go next to a high digit. So the moment we try to put 2 3s or 2 7s anywhere in these boxes, we're going to be forced to place, you know, the alternative digit next to it. Another way to think about it is we're going to need to fill these squares with digits. We're going to need 2 3s and 2 7s. So we're going to need to place 2 3s in 2 of them, and 2 7s, you know, in another one. I think I just said basically the same thing twice. But I think you get the idea, which is we're going to have to distribute the digits, but we're going to run into a problem when we distribute the 3s and 7s, because they're going to be forced into one whisper square together no matter what, no matter how we try to arrange it. Someone could probably prove that mathematically and say it more eloquently than I did. But that's the sort of the problem with placing these in the same 2 rows. So what that means is when we think about there's a whisper square here and there's a whisper square here, in this box we cannot place a whisper square in this bottom section, otherwise it breaks. So we're forced to place it up here, which is nice because this cage now needs a whisper square, which can go here, block things off, which forces a whisper square here, block these off, which forces a whisper square here, which forces a whisper square to finish this one here, which cascades up to here. And now either using cage logic or the fact that we just proved here, this whisper square has to go here. And now we've placed all the whisper squares. And this is the end of the video. I hope you enjoy. The rest of the puzzle turns into basically a German whispers arrow Sudoku. So you can think of this is kind of like an arrow that has a circle here and is the sum of these digits here, and similarly one here. And then we have all of our German whisper lines sort of lurking inside of all of these squares. And the rest of the puzzle is kind of taking this fact of, oh, there's a low digit here, so this must be a low digit. These 2 digits are going to be relatively high because they have one low digit and one high digit. So they're going to be something like 1, 2, and 7 or 8, and this is going to be an 8 or 9 forced by this. This 3 needs to be surrounded by an 8 and a 9, and this can't be a 9, so this is an 8, which makes this a 9, which bounces over here and makes this an 8. And the rest of the puzzle is kind of this bouncing around effect of figuring out where the rest of the numbers go. So I hope you enjoy, and good luck solving.